This is a example from class that we didn't get to finish because somebody was testing the generators, I think. We were looking at how to decide if a space, a vector space, is a linear space. And I promised you two methods. We did the first method in class already, but I'm going to recap it. I think the example from class was the example of the space of all complex vectors such that the first component plus I times the second component adds up to 0. So z comma w, that represents a complex vector, complex analog of the vector xy, if you like. So z is the first component, w is the second component, and the test is the first component plus I times the second component equals 0. So any complex vector that satisfies this equation will be part of the space S. And in set notation, we write it as S equal to, curly brackets, the collection of all vectors that come from two-dimensional complex space, such that, the vertical line represents the phrase, such that first component plus I times second component equals 0. More generally, the notation would be you'd have some vectors such that some condition is satisfied. And you'll need, so in this example, the condition is z plus iw equals 0, but in other examples, it's other conditions. So we had two ways to do it. I'm going to recap the first way that we did in class. So you'd have to look at two things. The first is if you take a vector from the space S and you multiply it by a scalar c, which you assume could be a complex number because z and w could also be complex. You want to know if that complex multiple of the vector is also in the space. So how do you decide? Is you take the first component plus I times the second component and see what it comes out as. If you get 0, then that multiple is in the space S because it satisfies the condition. If you don't get 0, then that constant multiple is not in S. More generally, you'd see if the constant multiple satisfies whatever condition defines the space. So let's see. First component is Cz plus I times second component, I times Cw. Take out C as a common factor. Z plus Iw we know equals 0 because the vector Zw is in S. So you get C times 0, which equals 0, and so we can conclude that that constant multiple is in the space S. We're halfway. The next thing you have to check is sums. You take two vectors, call them Z1, W1, and Z2, W2, and you see if they are in the space S. You don't see if they are, you assume they're in the space S, and then you add them together, call that result Z3, W3, for want of a better name, and you want to know if this new vector, which is the sum of the two vectors of these two guys, is this new vector in the space S? Well, that's the same as saying, does Z3 plus IW3 add up to 0? Alright. Note that by saying that Z1 and W1 are in S, we're saying that Z1 plus IW1 equals 0, and Z2, W2 is in S is the same as saying Z2 plus IW2 equals 0. So we can use that if we need it, and we will need it. So Z3 plus IW3, we want to see if it comes out as 0, and to do that, we use the fact that Z3 is Z1 plus Z2, W3 is W1 plus W2. We group the terms together in a useful way. Z1 plus IW1 will be equal to 0 because this vector Z1, W1 came from S, and Z2 plus IW2 will also be equal to 0 because this vector is in the space S. So we get 0 plus 0 over here equal to 0, and we conclude that the sum of two vectors in the space is still in the space. So we've got sums in the space, we've got scalar multiples in the space, and those two facts together tell us that the space S is a linear space. Option 2. You can do the two steps from option 1 in a single go. So what you do is you take two vectors, Z1, W1 and Z2, W2, and you assume they're in the space S, and instead of just doing a sum, you do a linear combination. In other words, you multiply the first vector by a scalar, you multiply the second vector by another scalar, and add those two things up, and call that Z3, W3 instead. So Z3 will be equal to alpha Z1 plus beta Z2, W3 will be alpha W1 plus beta W2, and you want to test it if that's in S, bearing in mind that alpha and beta are any old general complex scalars. So how do we test if Z3 and if the vector Z3 W3 is an S? Well, the condition is first component plus I times second component should add up to 0. So in other words, we want to see Z3 plus I W3, is it 0 or not? Well, Z3 plus I W3 is equal to, and we work out Z3 was alpha Z1 plus beta Z2, W3 was alpha W1 plus beta W2. You take out common factors and group things together in a convenient way. Z1 plus I W1 will be 0 because the first vector was in S, the space. Z2 plus I W2 will also be 0 because the second vector was also in the space. So that's alpha times 0 plus beta times 0, which adds up to 0. And so we conclude that Z3 plus I W3 equals 0, and therefore that linear combination must be in the space S because it satisfies the condition of the space. And that's it. From that we can conclude that S is a linear space because we checked sums and we checked scalar multiples in the same shot. That's it. That's the end of the example. The last thing I want to talk about quickly is just a couple of pitfalls that I've seen. So a couple of things for you not to do. One thing is when people construct Z3W3, they sometimes put it equal to Z3 plus IW3, which is wrong because you're saying that's like saying a vector equals a scalar, which is crazy talk. The second thing that we sometimes see is when you've got your vector Z3W3 and you want to know if it's in the space S, people write down the condition as if it's already true. And then they simplify the one side of the equation and get 0 equals 0. And from that they say, well, that shows that the vector is in S. Which is almost right, but we know what you're trying to say. But saying that Z3 plus IW3 equals 0 is not valid at the start of the calculation because you don't know if it's equal to 0 yet. So rather do it the way I did on the previous side, where you say Z3 plus IW3 equals, and you work it out, and equals, and you work it out, and equals, and eventually you get 0 or you don't. Alright. This equation here is wrong to say at this point because you don't yet know if it's true. Right? Stating this equation is a little bit like wishful thinking. You don't know it yet. That's it. That's the end of the example. Thanks for your time. If you've got questions, come to a consultation hour or office hours or whatever you want to call them.